And so of all of the videos that I've done from the last year's lecture, actually for 2 years now, the lectures have gone up on YouTube. This one lecture has been the one that's been viewed the most. From countries all over the world, this one's been viewed almost 2,000 times. And so there's something about this topic that confuses people. So I want you to ask questions. If you're looking at this going, wait a second, raise your hand, and that'll make this much more interactive, okay? So let's jump in. So what we're doing, this symmetry-adapted linear combinations of atomic orbitals, starts with something you already know. So start with a firm foundation of atomic orbitals. You know what an s orbital looks like. You know what a p orbital looks like. We're not going to do d orbitals, but you could extend this to d orbitals. Okay? And so it's useful for making these combinations of atomic orbitals, and that's where the molecular orbitals come from. Because if you think about where the electrons are in an atom, they're in the atomic orbitals. You bring these atoms together, and now the situation's changed, but they still sort of retain those mathematical relationships with their original nucleus, but they're just expanded, they're extended, and they're gonna add in combinations that, just like you add waves, they're either in phase or out of phase. They're gonna combine with these atomic orbitals and make a molecular orbital. They're gonna go over the whole molecule. So if an electron's in a p orbital on one atom and it gets next to a p orbital on another atom and they're in phase, it can move now between the two p orbitals. And so we combine those to make a molecular orbital. And the shapes look really different when they're generated by Gaussian, but we can just draw the two p orbitals in phase, and that would be good enough for our estimations. So reviewing back to the homonuclear diatomics, we went over to heteronuclear diatomics, now we're back to homonuclear diatomics. This is the d infinity h character table. And so we can look at these molecular orbitals. This would be the two 1s orbitals on hydrogen in phase with each other. We would draw them with the same shading, either unshaded or shaded, doesn't matter, as long as they're the same shading. And then we could walk through the character table. I've shown let's just look through these four rows and characterize this orbital. You know, I gave you that little spreadsheet, or not, that little flow diagram early in the semester to assign the Mulliken notation for these, where I said, stand on the origin and look up in the z-axis, and just looking up the same color as looking down. Yeah, yes, and so that would be z squared. Well, this is another way to do it. If you know the character table, point group, you can find the character table. So we know it's d infinity h, we go find that character table, and then we can look at those operations across the top. So those are the symmetry operations, and let's go through each column and operate on this wave function. And so if we look at this, that c rotation axis is the z-axis. And so if we rotate just 1/infinitieth of a turn, that's what a c infinity axis is, we just turn it slightly, has it changed color? The answer is no, because it's got rotational symmetry in this particular orbital. And so we get a +1 because we didn't change color. Everybody cool with that? We rotated a little bit around the z-axis and it doesn't change color, so we get a check mark by all four of those columns. So that column really didn't do much for us. But still, we know that we're thinking at least we've got the axis assigned correctly. Now we go to these vertical sigma planes, and these contain the principal symmetry axis. So any of the sigma v's and sigma d's, they're vertical with respect to the symmetry axis. So they contain the z-axis. And so this would be, let's just take the convenient one coming out of the board, reflecting the left and the right side of the molecule into each other. Does the color change? No, I see some nods, shaking heads. So no, it doesn't. So that's a +1 if the color doesn't change. And so that tells you it has to be one of these two rows. So you can use this character table as a filter. You can run this orbital through the character table and eliminate some rows and support others. And eventually this filter gets down to just a single row. And that's another way to assign the symmetry of a molecular orbital, is to use the character table and to operate through each of those columns on the orbital or on the wave function and see what happens. You could do the same thing with the arrows and the vibrations. If the arrow switches direction, then it's a -1. If the arrow doesn't switch direction, it's a +1. Okay, so let's go to the next one, inversion. So we invert this wave function through the center of mass, and it stays the same color. So it's going to be a +1 in inversion. So it's the top row, not the bottom one. See, so the top two are +1. The reason I didn't put a +1 on the second row is because it was eliminated in the previous column. And so now, just after 3 columns, I know what the symmetry of this orbital is. So you see the first column, I mean, E is always +1. So we can just kind of walk past E and go to the rotation. The first column operation, I had 4 rows possible. The second one, I had 2 rows possible. By the time I got to the third column, it had eliminated all the others, and we know that it's A1G. Okay. And we could continue on just to check our work. This is that the improper rotation where we rotate a certain amount and then we reflect it 90 degrees to that. So we rotate around the z-axis and then reflect it, and we can see the orange exchanges with the orange, so it's still the same color. And then the last one are the C2s that come out of the axis, the principal symmetry axis at 90 degrees. And so we're taking the top of the molecule and rotating it into the bottom. Again, same color, +1. So that whole row is supported by all of these operations on this wave function. Now, the reason I've eliminated the others, that put blue boxes over them, is you can really only do this method for the singly degenerate rows. So A's and B's. So in the character table, you want to write that down. You can use this method of working your way through the character table only if it's an A or a B Mulliken notation. The E's and the T's are doubly and triply degenerate. And so it's really hard to work your way through those rows. And so if you try it, and it happens to be an E or a T or whatever, you try it, you're not going to get a coherent answer. You know, it won't be all of the answers on the single row. You'll get some answers on one row, some answers on another, and you won't have any answers. So that means it's probably an E or a T. Let's do it for another one. So let's go on, and so this ends up being z squared. We could have gotten that from that little flow chart. You know, if you stood on the origin, you looked up and looked down, it was z squared. If you looked left and right, it was y squared. You looked forward and back, it was x squared. And so you would have gotten the top row either way. So the flow chart's much faster, but I just wanted to see how you could show you how you could use the character table and you work your way through it. Okay, so let's look at this one. Let me go back. So this is the molecular orbital that's oscillating up and down on the z-axis. The last one was oscillating out and in on all directions. This one's oscillating up and down on the z-axis. So it has z symmetry, so we already know it's going to be that one down here that has z. So if you know, I mean, you don't have to do this, but if you ever get confused, you can prove it to yourself and say, okay, I think it's z. Let's go through all of these operations and just check my work. Okay, that way you can be really confident that you know all there is to know about this orbital. But let's go through this. We have a rotation around the symmetry axis. Again, the orange stays where the orange is and the blue stays where the blue is if we're rotating around the z-axis. And so we get a +1. The sigma v's, we're just taking the left and right sides of the molecule and reflecting them into each other. Again, they stay the same color, so it's a +1. Now inversion, we invert that wave function through the center of mass and the colors change. So we get a -1. And so then that eliminates that top row. Up there we had +1, +1, but now we have a -1 under inversion. And so that drops us down into the lower half of the character table. And then we can do the improper rotation. We rotate a little bit and then reflect through, and the colors exchange. So we know that's a -1. And then any of the C2 axes that are coming out 90 degrees to the principal symmetry axis would flop the colors. And if the colors flop, you have a -1. So that's going to be Z, and it's going to be A1U. So that's how you can use the character table to identify the symmetry of a molecular orbital. And so then we can put these in a molecular orbital diagram like we showed last time, where the one with the larger box and no nodes is stable, lower in energy, and then the one that has, even though it's got a larger size for the orbital, it's got more curvature because of the node, and so it's going to be higher in energy. And so this, again, is the simplest molecular orbital diagram. Just have 1s orbitals. It's hydrogen. But let's go through and take a Kahoot on the last set of the notes, where we're identifying what atomic orbitals go into a particular molecular orbital, and then also what kind of bonding arrangements we have. So this first one is really on the bonding in a molecule, whether it's a sigma or pi bond. (324, 270). One more. We lost our pumpkins. Okay, ready? All right. Got to start it before your phone goes to sleep. Describe this orbital. Dun, dun, dun. All right, this is a sigma or a pi orbital. Come on, 100%. Oh. Sigma. All right, what makes it a sigma orbital? Rotational symmetry. Right? So here's the bond in the middle. You can spin it around and it doesn't change color. It's a sigma. Bonding or antibonding? Antibonding, very good. You know that because there's a node that breaks the bond. Okay. Let me get into some more complicated things. So we have combinations of sigmas and bondings, and pi's and bonding. Very good. It's pi. It's a pi and a bonding orbital. So pi is side-on interaction. These are p orbitals, and there's no node in between. So that's Come on, 100%. I believe in you. Some people are just trolling me, I know. Now, there is a node there and so the node is not the gap, the node is the different plus and minus. Okay, like the last one had a gap in the middle, but they were the same color. They were plus and minus together. And so even though we have an air gap there, I mean, really that's just showing you just the atomic orbitals. They would like squeeze together if they're the same shading. Oh boy. Oh, so close. Okay, so this one is, again, it's got rotational symmetry. The bond is right there in the middle between the plus and the minus. So if you spin that, it would stay the same color no matter what. And that would be a sigma interaction. And then this change in sign in the middle is antibonding. So there's a node there that breaks the bond. This is for a diatomic. So the nucleus is here on one side and here on the other side. So these are PZ orbitals. How do I know it's PZ and not X or Y? Bonus question.
Because it's the
Yeah, so diatomics, the z-axis is always the axis of the bond. Because that's the principal symmetry axis. Pretty obvious which one this is, even if you're just doing it statistically. going to take a picture of it if it's ever 100%. But, so they, again, for the one who missed it, this is a sigma interaction because, again, rotational symmetry, same color all around, and it's bonding because these are the same sign in the middle. Same sign, same shape. Bond order. So this is a little tough to see this diagram. It's too small. Okay, there are 2 electrons up here that are unpaired. 2 unpaired electrons right there. So this bottom is sigma, sigma star, sigma, pi, pi star, sigma star. Hurry, hurry. Oh, pretty good, even though you couldn't see it. There's the picture, yeah. Okay. 2 unpaired electrons up here in the pi star. Yeah, I'm sorry. Okay, it's a good thing I don't count your grade. It's just that you participated. But you're losing your streak. It's like, all right, is this molecule paramagnetic or diamagnetic?
Is that the same one?
Same one. So we had those 2 unpaired electrons in the pi star orbital. Found something you didn't know. People were like, yeah, about a 50-50 split, not quite. Okay, so this is, again, unpaired electrons. Those are like little magnets. And so if they're paired, the magnetic fields cancel out. If they're unpaired, the magnetic fields don't cancel out. And so then that makes this molecule magnetic, paramagnetic. So if you put it in a magnetic field, it will have some interaction with that magnetic field. It makes it very difficult to do NMR on these molecules because
So what is dimagnetic?
then it's the paired up. So no, yeah, so non-magnetic. Yeah, I don't know why they use para and dia. Yeah, exactly. No idea. So 9 out of 10 here. What's the multiplicity of this molecule? Same molecule. Same molecule. What's the multiplicity? Some great faces. Yeah. So 2 unpaired electrons. What's the net spin? Each of those has a 1/2. Yeah, what a spread that is. Okay, so 2 unpaired electrons, the net spin, you add up the unpaired electrons, so it's 1/2 plus 1/2 gives you 1. All right, and then the multiplicity is 2 times that plus 1. So 2 times 1 is 2, plus 1 is 3, so triplet. The other way, the shorthand way, is however many unpaired electrons you have, just add 1 to that. So 2 unpaired electrons, add 1, that's 3, triplet. Okay, so. And then finally, this molecule is neutral, therefore it must be, dun dun dun. I had to tell you how to tie the electrons to the identity of the molecule. So. 2, 4, 6, 8, 10, 11, 12. Quick, math. All right, well, the majority got it. Very good. So, and plus this one, this hopefully through working these problems, you'll be so familiar with the second row diatomics that you could just hammer them out. I've got 2 more electrons in that antibonding orbital. So if I keep adding electrons, I'm going to get fewer and fewer bonds, right? Because I'm putting electrons in the antibonding orbitals. So what arrangement would be the most bonds I could get? If I got rid of those 2 electrons, I'd have a triple bond, right? Which molecule has a triple bond? Nitrogen. So dinitrogen has a triple bond, and this is 2 electrons past that. So I'm starting to populate those antibonding orbitals, which means I'm past nitrogen, and I'm over to oxygen. If I add 2 more, I've got fluorine. If I add 2 more, I've got dineon, and that doesn't exist. It's a bond order of 0. So I've gone past the maximum in terms of the bonds and bond order, so I'm past nitrogen. If I were below it, if I take off those 2 electrons, it's isoelectronic with nitrogen. If it was a neutral molecule, it would be nitrogen if I took away those 2.
But if it's nitrogen, wouldn't the pi bonds and the sigma bonds have to be flipped into that diagram?
Yeah, that's true too. So the ST mixing would be, yeah. Nice touch. All right. What's this? Oh, okay. Wow, I got a little song. This is like my favorite game on earth, and that is, you know, the Mario Kart. Man, I love that with the cloud and everything. My kids are like, skip past it. I was like, I like the party at the end. It's fantastic. I'm watching the whole thing. They're like, ah. So, all right, good job. Yeah. Okay. So let's dive back in. Let's now look at the projection operator. So what we were doing with this, with these orbitals and going through the character table once we had the orbital, is sort of the projection operator in reverse. Okay. The projection operator is. Wait, I must do that. Okay. Good. My hearing's not completely gone. All right. What do I got to do to get feedback? Okay, very nice. All right, thank you. And so let's look at the projection operator, and it uses the character table, but it does what we did. We were doing the projection operator in reverse. So this now takes definitions of the atoms in a molecule and runs them through the character table. And if you think about what's going on in our projector, okay, it has a light source, and then it has some sort of element that has the image information on it, and the light source goes through that imaging element and shows up on the screen. And so that imaging element up here is controlled by the computer and everything. The imaging element for our molecular orbitals is the character table. So we take the molecule, we define those orbitals, and we run that molecule through the character table, and on the other side comes out all of our molecular orbitals. Okay, so that's what we mean by projection operator. It's a mathematical projection, but it's kind of like you use projections when you did trigonometry, where you're looking at the you've got the catapult problem, and the projectile's coming off at an angle, and you have the angle and you have the hypotenuse of the triangle, and you project down to get the x component. So you're looking at the shadow of that vector. And it's the sine of the angle times the hypotenuse. And you've got the projection of that vector straight down onto the x-axis. And you can look at the vertical projection and get the vertical component. So we've done projections before. Same kind of language. I like to use the projector analogy because that sets up the character table as the imaging element, and the molecules projected through that. The atomic orbitals are projected through that, and out on the other side come the molecular orbitals. And the neat thing about that is not only do you find out what symmetries the atomic orbitals make for the molecular orbitals, you also find what symmetries are impossible. So you get both the light and the dark regions. You say, okay, there are orbitals with these symmetries, and I can prove there are not orbitals with those symmetries. So you get everything. So let's walk through it. It looks really ugly. It's an equation that's been just pulled right out of the symmetry book that I didn't assign for you. But Cotton and Wilkinson's Chemical Applications of Group Theory has this book. So if you wanted to know about that book, it's F.A. Cotton, and it's Chemical Applications of Group Theory. And so let's just walk through the pieces of this equation. So it's saying that this P here, this beginning of this equation, is a projection operator operating on the wave functions. These will be the atomic orbital wave functions. And what it's going to give us is the symmetry of that combination of atomic orbitals. And so this projection operator, P of gamma mu, so gamma mu, that's these different Mulliken notations. And then it's going to be the sum of the character. So these are the characters, right? These green things are characters. that are under the operation. O is for operation, operating on the wave function. So those are the 4 pieces. The wave function is being operated on. That's the different columns. And it's going to be a product of the result of that operation times the character. So we have 2 pieces. We have the operation piece and we have the character piece, and they're multiplied by each other. And then we have the sum piece. We're going to add them all together. So this is going to be the sum of a bunch of little pairs of multiplications. Okay. Now, we could do this on the wave function, but what a mess of math that would be. So we're just going to use the notation like 1s on atom A and 1s on atom B. But that represents the whole, 1s orbital in 3 dimensions. Okay. But we'll just use that little notation, 1s on atom A, 1s on atom B, as our wave functions. And so let's walk through this one piece at a time. So we'll start with the top row. So we do this for every row in the character table. Again, this is a projector, so we're projecting through the character table, so we've got to take into account every row. This would be really tedious to do, but we'll just do a couple of examples in today's lecture, and then you'll see how the molecular orbitals are created. So for the A1 row, so you see that right here, we have the A1 row right here. And if we operate on that 1s orbital on atom A, and we do an E operation on it, what happens? Nothing, right? That 1s on atom A stays on atom A. And so all we're really looking at is, does that orbital move over to atom B, or does it stay on atom A? That's really the only question. And then we put the character in front of it. So we operate on that 1s orbital on atom A, and it stays on atom A, and we have this +1 in front. This +1 comes from that right there. Okay? Then on the C2 axis, so this is for water. We're just looking at the hydrogen orbitals. So for C2, on the top row, if we do a C2 on this molecule, notice atom A moves over to atom B, and atom B moves over to atom A. Does everybody see that? That's the C2 operating on the 1s orbital. It's moving it over to atom B. And so the C2 piece gives us this. We do a C2 on the 1s on atom A, and it becomes 1s on atom B. So that's the C2 part. The character part's in front. The +1 goes right there. Okay. So we have the operation piece that gives us the 1sB, and we have the character come down. That's the +1. Okay. And then that sum is where we're adding these things together. Okay. Then we do the third column. We do a reflection in the XZ plane. You see the XZ plane here? And that moves the left side of the molecule into the right side, and the right side into the left side. So if we do a sigma XZ, the 1s on atom A goes over to B. And so we end up with 1sB. And the character in front is a +1. And then we do the last column, YZ. So the YZ plane is the plane of the paper. And so 1sa stays put if we do a reflection in the plane of the board. Okay. And so then we have 1sa here, which is the result of the operation. And then we have the character in front of it, a +1. Notice I have a +1 on atom on one +1sa, +1sb, and then we repeat it again, a +1sa, +1 sb. And so if we were to normalize that, this normalization constant, we would have like 2 times 1sa plus 2 times 1sb, but that wave function wouldn't be normalized. So we could normalize that, and we end up with this 1 over the square root of 2. But the bottom line is we have a plus in front of this one and a plus in front of that one. See, all of these are pluses. And so the symmetry adapted linear combination, that's what we're doing. We're adding these orbitals together. That has the symmetry of A1 is just 1s on atom A in phase with the 1s on atom B. But that comes from the projection operator. Okay, this one was pretty simple. Let's look at the A2 and we'll see how it cancels out. Okay, this is a little bit on the normalization. Let me just show you this real quickly. You know, we had this situation where we had CA and CB. We can pull that out to C total. And then C total is 1 over the sum of those individual coefficients squared. And so we had 2's come out, and so it would be 4 plus, it'd be 1 over the square root of 4, so 1 over the square root. Oh, I've screwed that up. Work your way through this and you'll see that's where this 1 over the square root of 2 comes from. And later on we'll have this situation with ammonia, and we'll see that we end up with 1 over the square root of 6 times this. Let's do the A2 example. So we're operating still on the 1s on atom A. I've got the E column written here. We have a +1 for the character, and we're doing this second row, A2. If we do the C2, we get 1s on atom B. And so the A's and B's will look just like the previous example, but the only thing that will change will be those coefficients, the +1s and the -1s. So under C2 for the second row, we have a +1. Under the sigma xz, we have a -1, 1sb. And then under the sigma yz, we have a -1. So look what happens on this one. I get a +1sa and a -1sa, a +1sb and a -1sb. So this tells me there's no way to combine these two atomic orbitals in this point group with the A2 symmetry. So not only do we get the positive result of an A1 symmetry combination, we get the negative result of no A2 combination. So this is using that character table as a projection. It will tell us there are no A2 atomic orbitals combinations. And there are going to be no A2 molecular orbitals. So we take those atomic orbitals, run them through the character table, and this will tell us what symmetries come out on the other side. Let's do the B. We can probably speed up a little bit because you can see that the A's and B's don't change, only the characters in front. So this one has a +1, 1sa, a -1, 1sb, a +1, 1sb, and a -1, 1sa. And so the B1 cancels out. And so there's no way to combine the 1s orbitals on these hydrogens in water in a C2v character table to get a B1 symmetry. Now doing the last one, I bumped the little screen up so we can see the last row. So +1, 1sa, -1, 1sb, -1 again, 1sb, and a +1, 1sa. So looking at those, notice all the A's are positive and all the B's are negative. Normalizing that, we get the 1 over the square root of 2, and so then we have the out of phase combination of 1sa and 1sb. Now for two orbitals, we really didn't need to do this. You know they're either in phase with each other or out of phase with each other. But the nice thing about this is it tells you exactly which row those are going to be on. So, and this is exactly how Gaussian produces these orbitals. It knows the point group of the molecule, and it can go through and project the different combinations of the atomic orbitals, and it also knows then the symmetry of the molecular orbital that it's producing. So these are the symmetry-adapted linear combinations of the hydrogen 1s orbitals. We have the 1sa in phase with 1sb and the 1sa out of phase with 1sb. Now looking at the oxygen valence orbitals, we have the 2s orbital, which is going to be top row, and we have the 2p x, y, and z. Now those are really easy because you get the designation x, y, and z. They tell you exactly what row they're on. And so then we can combine these because remember, orbitals of the same symmetry combine. And so we know that the 1sa the 2s is an A1, and the in-phase combination of the 1s orbitals is A1. So those will combine in phase and in out of phase combinations. And so we have our sigma and sigma star for the lower one, and then we have three orbitals, and so they're going to be combining in a third way up here. We have that PZ coming in as an A1. So we have three orbitals coming in and combining to form three molecular orbitals. If I were to draw these myself, I wouldn't have, the detail that Gaussian has. So I combine them in phase and out of phase for the 1s orbitals and the 2s orbital, and then up here the 2pz orbital out of phase with the hydrogens. And so then I see my nodes. I've got a node there, a node there, a node there. So there's 3 nodes, there's 2 nodes here, and 0 nodes. And so this would be acceptable pictures for you to look at the different orbitals and how they combine. Yes?
So why does the PZ for oxygen lend itself to the 2 sigma star?
It's just got the same symmetry, so some of it will mix. It's not much down there because they're pretty far away from each other in energy, but it does. It's just showing that they have the same symmetry, so they mix to some degree. Yeah. And you see, it is kind of compatible with that orbital. So, there's a different color on top than on bottom, and so that can come in and combine with those. And then let's look at the other ones. We have B2, and B2 is the 2py atomic orbital, and B2 is also the 1sa minus 1sb. And so those are going to combine in a bonding and an antibonding arrangement. Now the antibonding arrangement on water here is pretty complex. So if I were to draw that myself, I might do something like this. Just to show clearly that's the 2p y orbital, and then the 1s orbital's out of phase. And so they're out of phase with each other, so that's going to be the antibonding arrangement of those. And then the bonding arrangement would be, if I swap these colors, then the blues would be on the same side and the reds would be on the same side. So one would be bonding, one would be antibonding. This is clearly antibonding because the node breaks the bond. Okay, and so you could say we really only have 2 types of bonds in this molecule, so it is pretty clear in water that you could say this is a totally antibonding orbital, and the one below it up here is totally bonding. Remember with the ethane or ethene, it was unclear because you might have a bonding arrangement for the CH and an antibonding for the CC. So if you have different types of bonds, you need to talk about which type of bond it supports and which type of bond it harms. Makes sense? So if there's a node that breaks that bond, it's antibonding in that particular association, and if there's a lobe that covers that bond, it's bonding for that type of situation and supportive of that bond. And then the last one is the 2px orbital. It's B1, and we went through the projection operator and made our symmetry-adapted linear combinations of the hydrogen 1s orbitals, the SALC-AOs, and we didn't have a B2. I'm sorry, we didn't have a B1. And so there was no B1 for that combination, and so there's nothing for the px orbital to bond with. And so I've rotated it 90 degrees so you can see that it's above and below the plane of the hydrogens and the oxygen. And so there's nothing for that orbital to interact with. So it just comes straight across. It doesn't have any lines connecting to it on the hydrogen side. So that is the projection operator for water. That's where these pictures come from. We have an energy level associated with every molecular orbital. We come in with 8 total valence electrons, and we start at the bottom and build it up. Let's do the same thing for ammonia. Let's go kind of quickly through this one. It's the same story. Now, before we go on, though, let's look at this. Look at this character table and compare it to the ones you've seen before. In the C3V character table that I hand out, there's only 3 columns, if you'll notice. And in fact, those 3 columns are captured by these combined headings. You have an E, you have this 2C3 column, and a 3 sigma V column, and it's been condensed. This is the expanded character table. When it says 2 C3s, I could go clockwise 1/3 of a turn or counterclockwise 1/3 of a turn. So those are the 2 C3 axes. Since they have different results, A goes to B versus A goes to C, then they're really 2 different operations. And the same with the sigma V's. There's 3 sigma V planes. And so they each have a different operation. So in the projection operator, we pay attention to every one of those, even though they have the same character. And let's just quickly go through it. This is more for enrichment, just following through how we build these molecular orbitals. So we've got the different projection operators, one for each row. Then we have the characters, and then we have the different orbitals that we're operating on. So let's pick on the 1s orbital on atom A, and we'll make the symmetry-adapted linear combinations for the hydrogen atoms. And so it's a little bit long, it's 6 terms, because there's 6 columns in the character table. But if you look at this, we're working on the top row. We have the characters, and we have the wave functions. And so if I do the E operation on the 1s orbital on atom A, nothing happens, it stays put. And what's the character in front? It's a +1. If I do a C3, so we're going to do this looking down at the molecule, we're going to do a like clockwise turn looking down at the molecule. So the 1s on atom A now is moved over to C. And so that C3 operation gives us this 1sC, and the character in front of that's a +1. Then going the opposite direction, we put it on B. So atom B, the 1s moves over to, on atom A moves over to 1s atom B, and we have a +1 in front of that. Then all of the different sigma planes. So the first one contains 1sa, okay, so it stays put. The other one is this plane out this direction, so it reflects 1sa over onto 1sc, and so that's why it becomes 1sc on the sigma V prime. And then the third plane is back here containing the 1sc bond, and so A becomes B. So do you see the 3 planes moving A around? It either stays where it is or moves to C or moves to B. And then we have the character in front of each one of those, +1, +1, +1. Now if we look at this, all of them are added up. We have 2's in front of all of them, so we end up basically all of them in phase, 1sa plus 1sc plus 1sb. And so that's going to be this all 3 orbitals in phase with each other. Let's look at A2. And so we project around. Now the one thing that's the same in all of these is these 1sa, C, B, A, C, B. Because that's the effect of the columns. The thing that's different is that the characters change. And so now we have 3 +1s and we have 3 -1s. So we have a +1, +1, +1, and -1, -1, -1, and those all cancel out. And this tells us there's no possible way to combine these 3 1s orbitals to give us an A2. This will be the last thing we do. We run through the E column, or the E row. We have the same A, C, B, A, C, B. But now the characters tell us under E, it's doubly degenerate, so there's a 2, and a -1, and a -1. So this tells us that the 1s orbital here has a magnitude of twice the others, and the others are out of phase with it. And so we could take this and we could draw that picture. And we could say that the 1s on atom A is big, and the 1s on atom B and C they're the same. And so you can see that there's sort of a red side of the molecule and a blue side of the molecule. And that's going to be one of the symmetry-adapted linear combinations for the hydrogen atoms. Now, what orbitals on nitrogen is this going to interact with? The p orbital that goes this direction, right? And so that's going to be a molecular orbital when you combine it with the p orbital on nitrogen. But we have to do the symmetry-adapted linear combinations of the atomic orbitals to to make the molecular orbital. And so that's where we get these pictures. We'll zoom ahead. We see the top one was A1. There is no A2. And then the E is this one here on the left. That's kind of what I've drawn. Actually, it's this. Yeah, it's this one on the left. Kind of what I've drawn, looking down. And by elimination, if we've used the 1SA twice, it's got a twice a magnitude. It will be used 0 times in the other component because it's E. That means it's doubly degenerate. So you've only got one of those. How do you find the other? A is used twice, and so it'll be used 0 in the other one. B and C are the same sign, and the other one they have to be the different sign. That's all it is in this symmetry-adapted linear combination. So you have this setup for the E's. So we have the 2S, 2 on 2 times the 1SA, and then minus 1SC minus 1SB, and then this one is opposite sign for the 1SC and the 1SB. So that always works out in these different combinations of 3 things to make 2 things. You use one of them twice, and you use it not at all on the other, and then you have the same sign and then the opposite sign. So that's the projection operator, and that's where these molecular orbital pictures come from. So what do you need to do? You need to be able to, if you're given a molecular orbital picture, you need to be able to assign a row. So you should be able to do that pretty easily. Now the level up, you want to level up, if you're given this designation here, can you draw the pictures? So that's the next level. If you're just looking at the coefficients in front of those different things, you should be able to draw the pictures. I've got a 1s orbital that's twice as big, and it's the opposite sign of the other 2. I should be able to draw that picture. All right, so that's a good place to stop.